Good afternoon. Welcome to SGX Secure Enclaves in Practice, Security and Crypto Review in South Seas GH with Jean-Philippe Omasson and Luis Marino. Before we begin, a few brief notes. Stop by the business hall located in Bayside AB on the first level. The Black Hat Arsenal continues to be in the Palm Foyer on level 3, and of course the Arsenal reception will be today at 5 o'clock p.m. If you haven't picked up your merchandise, today is your last chance to visit the Black Hat Swag and Bookstore. Visit the Kali Linux Lab in Mandalay Bay A. Please also put your phone on vibrate. It makes it easier for the rest of us to ignore it ringing while you wait for your voicemail to pick it up. Without further ado, your speakers.
Thank you. Okay. So, good morning. So let's talk about SGX. You probably know that SGX is the new security technology and Intel chips. And that's the first public review of SGX based on actual hardware. So actual Intel chips that implement SGX, and on the real SDK. So just spoiler, we're not revealing any big ODA or vulnerability. So if you don't like it, you can leave the room. But I hope it will be interesting nevertheless. What we'll show you is some undocumented parts of SGX, so stuff that is not publicly disclosed by Intel, and we're releasing some tools and some applications. All right. So I'd like to thank some people who helped us, gave us some useful feedback. So the folks at Intel, Shai Geron, Simon Johnson, Dan Zimmerman, also Victor from MIT, who did this great paper about SGX, Samuel Neves, who helped us with the crypto, and Joanna and Arrigo gave us some useful tips as well. Okay, so what is SGX concretely? So it's yet another new extension of the x86 implementation of Intel. And it's mainly two instructions, so enc-ls and enc-lu. So enc-ls can only be called in kernel mode, and enc-lu can be called in user mode. What is this good for? So they will allow you to create secure enclaves of code and data. So what does that mean? A secure enclave is a piece of bytes. The bytes can be code, can be data. And you can use this to run a trusted program. So trusted, what does it mean? Is that you can execute some piece of software on someone else's computer with the guarantee that the execution, the integrity of the execution is protected. So the code executed is the one that you expect to be executed. And it also guarantees the confidentiality of the secret data that you attach to the enclave. The confidentiality means that only the CPU will see the clear text, not the OS, not the hypervisor. We'll go back to this. Okay. So using these two instructions, you have actually a bunch of instruction leaves or sub-instructions. For example, eGet key can be used to derive cryptographic keys within the CPU. So without any other component seeing those keys. You have eReport, for example, that can be used to create a kind of identity of your enclave. So if you want to play with this, you can buy one of the Intel CPUs using the Skylake microarchitecture. They came out first in autumn 2015, but you have to make sure that you also get the laptop and the BIOS that supports this. Okay, so maybe when people ask me to explain SGX, maybe the easiest way is to see it as the inverse of a sandbox. So a typical sandbox, it isolates an application from the system, whatever that means. So you're trying to protect your application from the system and, I messed it up. You're trying to protect the system from your application or to protect other applications from your own application. So you're trying to isolate your system. SGX is the other way. You protect your application from the system, from the external world. Okay. So when I say the system, it can mean the operating system. It can be an hypervisor. It can also be at a lower level, BIOS firmware drivers. Even at a lower level, what is sometimes called ring -2, the SMM, system management mode. I won't give all the details, but you can see it as a piece of software that sits between the BIOS and the OS. And it also actually protects from a compromise of the Intel ME management engine, which is sometimes called the ring -3. And you can see it to simplify as a kind of CPU in the CPU, if you will. So by extension, it will protect your application. So remember the integrity of your program and the confidentiality of the secrets that are attached to this program. It will protect everything from any attacker, any remote attacker that would compromise any of those pieces of software hardware. So that's pretty powerful. One of these applications is cloud computing, cloud services. Just one super basic example. Imagine that you're using a word processor that's running not on your machine, but on one machine in the cloud. You're editing a document, so everything happens on a remote CPU. But the guy on the admin of the other machine, the operating system of the other machine, he has no way to see what you're doing, the clear text of your document. Okay. So another application is DRM. So I've sometimes heard people saying, yeah, SGX is bad because it's a DRM. No, it's not a DRM. I want to make it clear. It will help you to create a DRM. So the whole point is that instead of trying to hide the content decryption key in the software, use the obfuscation and other techniques, the key will be just inside the CPU, if you will. So there will be nothing to reverse, nothing to deobfuscate, because it will be a totally different game. It will be inside the CPU. Okay. Another killer application is to make programs that are literally impossible to reverse engineer. So instead of saying some code that is packed, obfuscated, partially encrypted with the key hidden somewhere in the software, you will just send an encrypted blob that will be decrypted on the CPU, and the CPU will act like a kind of virtual machine and run your code. One way to realize it is to have an enclave generate a public key pair, so private key and public key. It will keep the private key for itself, and it will send the public key out with some evidence that the public key that you receive actually comes from this SGX-enabled CPU. So what you will do, you will use this public key, encrypt your program, and send it to the CPU, which will decrypt it and execute your code. So there's nothing to reverse engineer. But now the first reaction of everybody is, oh my God, the bad guys, they will make super malware that is impossible to reverse engineer. There's just one small caveat here, is that in an enclave, you cannot do syscalls, you cannot do I/O, and you have a limited set of instructions. And the program, it can only run in userland, not in kernel mode. So you need some privileged escalation if you want to get through it. So that's not new. So the implementation of Intel is new. That's great. But the idea of trusted computing dates back to at least the 80s with the Orange Book. So trusted computing, to make it super simple, again, it's the idea of using someone else's computer with integrity, confidentiality guarantees. And to implement this, you need to implement several concepts to define several notions. At least trusted computing based, TCB, hardware secrets, you need remote attestation, sealed storage, and memory encryption. So I'll briefly go through the first three of those. So trusted computing based, the TCB, is the components that you have to trust to benefit of the security of the whole system. So in Intel SGX, the TCB consists first of the CPU itself, the physical CPU, so its physical package. So what's inside, you have integrated circuits, you have microcards, you have registers, cache, and a bunch of other stuff. And the TCB also includes some software components. So Intel minimized the number of the size of software in the TCB, but in particular, you need one piece of software that is called the code enclave, and you can see it as a kind of the software that will create the equivalent of a public key certificate, but for SGX. This is called a quote, and I will go back to this later. So many people are like, oh, but I don't want to trust Intel, you know, they're blah, blah. But man, you got to trust Intel anyway. It's running your code. If you don't want to trust Intel, then you can use something else. There's just one small caveat. So you have the TCB, the stuff you have to trust. But when you're creating the enclave, when you're building the enclave, you need to trust the whole system. Not just the CPU, but your compiler, your operating system. And you should read this paper if you don't know it already. Now, how are there secrets? It's very simple slides. So you got a CPU, and in the CPU, you have, when you buy it, you get two hard-coded secrets of 128 bits. So you can say that's like a root of trust. So the first one is called the provisioning key. The second one is called the seal key. You don't have to remember this. But the important thing is that the second one is not known to Intel. So Intel doesn't know any of those keys in any of the CPU. So again, you've got to trust Intel. Oh, maybe they're lying to us, and maybe they're blah, blah, blah. But OK, you have to trust someone. And the important thing to know is that all the cryptographic keys that are derived in a CPU, they depend on this seal key. So the seal key is used as an argument, and if you don't have it, then you cannot determine the other keys. Okay. Some intrinsic security limitation of SGX. So it's not a magic box. If you have insecure software, it will not make your insecure software secure. So specifically, if you are vulnerable to cache timing attacks, you will still be vulnerable to cache timing attacks when running using SGX. So maybe the attacks may be a little bit harder, maybe a little bit easier, I don't know, but it won't fix your problem. So it's the same if you have memory corruption or race conditions or the usual stuff. You have no guarantee against physical attacks. So if someone gets your CPU, decaps it, runs some I don't know, laser attacks, then Intel doesn't give you any guarantee against this. And then finally, microcode patching. So SGX depends largely on microcode. So if you are somehow able to patch the microcode, which is very hard because it's signed by Intel, then you may modify the behavior of SGX. And even if you're super smart and you manage to do it, you still need to gain persistence, which is also very hard. Okay. Now you want to find bugs in SGX, you want to break Intel's technology, you want to give talks at Blackout. So nice thing for you is that the attack surface is huge, it's super complex, there'll probably be many bugs. But the bad news for us is that it's mostly a black box. You don't get to read the actual microcode. Even if you get to read the microcode, you have to understand what it means. Many of the important instructions, so they are in microcode and they're not fully documented. So the best way to try to find vulnerabilities is just black box testing or fuzzing, if you can do this. Good news for the security researcher is that a large part is software that you can look at. The platform software, the drivers, the Intel Enclaves that are used to make SGX run, and the SDK, so the libraries that you can use and statically link to your own software to use in SGX. Okay. So for example, Intel disclosed some bugs, not the whole details, but some CPU bugs. It's written no fix, so I guess it means that it will not be fixed, but I don't really know the implications of this. You may also have bugs in dependencies, so at some point SGX software uses some small part of OpenSSL and some part that happens to be vulnerable to some high severity attack. As far as we could tell, it's not exploitable, but that gives you an idea of the kind of stuff that can go wrong. So can you recover from a compromise? Can you patch it? Yes, you can. You can upgrade the TCB, which means you can have a new version of the critical enclave. You can have a new version of the microcode. And also the nice thing is that when you perform the remote attestation later on, you will check the version of the TCB. So you can say, oh, I will only run on the latest version of the TCB, not on the insecure one. But the hardware cannot be patched. The memory encryption engine, which is in hardware because it needs to be super fast, you cannot patch it, so I hope that they tested it correctly. So now I'll give the mic to Luis.
Thank you. So we wanted to try this. Our setup is composed by a couple of SGX-enabled laptops, 6th generation. You also need to get support from the BIOS. It's not only the processor, but you need to enable the technology on the BIOS. If you are working in Windows, you need Visual Studio Professional 2012. That is not free, but you can get a free trial for 1 month. And you will also need to download the platform software and the SDK. I will explain more about this later. Now, you can also get the Linux SDK. It's ready. It was released 1 month ago. You can go to GitHub. You can get the SDK, the platform software, the drivers. You have to compile them, and you can get them ready. At the moment, only Ubuntu 14.04 is supported. Maybe you can make it run somewhere else, but you might want to know this. So now, this is a warning. SGX is about trust. You don't only need to trust the technology, but you also need to trust the supply chain. When you go to download the SDK, the website is running, the connection is running through HTTPS, but when you click on the download, the connection is in plain text. So somebody in the middle might modify the tools you are using to build secure enclaves, and you might not know. Also, when you get the installer, the certificates were expired. Now it's fixed, but there are some concerns in the whole supply chain, in the whole environment, that you might want to evaluate. So what do you get? You get a couple of things. The platform software is required to run enclaves. The technology is super complex, so you need the processor to cooperate with a few privileged enclaves that will make everything happen. Some of these are the launch enclave that will enable your enclave to run, the quoting enclave that will enable the remote attestation, and a couple more that cooperates also with the provisioning, and something else that I still don't know. So you also get a system service, some drivers, some DLLs, and also the Intel privileged enclaves, they have some superpowers. They can access some of the hardware keys that nobody else can. They are signed by Intel, they have this privilege, so if you break into them, you might compromise the security of the whole technology. On the Linux binaries, you also get the symbols, so it's easier to understand what is happening. You might not be allowed to reverse it, though. Also, the SDK, it's around 170,000 lines of code, BSD license. You also get a new standard library, so you are not using the one from the system that is based on OpenBSD and NetBSD, and some more dependencies. What do you get with the SDK? The SDK is mostly required to build SGX enclaves. And on one side, you get libraries. You get a new standard library. You get some crypto libraries. And then you also get some SGX libraries that provide the whole functionality. And they come in debug and release mode, with and without symbols. You also get a couple of tools. One is the Edge writer that will generate glue, so your application and your enclave can easily communicate, and it's C code. And you also get a tool to sign the enclave. You need to have a developer key, okay? This key, you can generate it, and you can use it to play with the technology, and you will use this key to sign your enclaves. And the signature will be checked every time you want to run the enclave. If the signature doesn't match, the enclave will not be allowed to run. You also get some example code. It's not fully complete, and it's not fully reliable. So if something doesn't work, maybe it's not your fault. You also get a debugger. The debugger can be used in Visual Studio, in debug mode enclaves, and you can also use GDB. Release mode enclaves cannot be debugged. You cannot hook a debugger, you cannot place breakpoints inside, and every time you try to call the enclave, it will be seen as a big instruction. You cannot tell what is happening. You cannot see the memory inside. You cannot trace what is happening inside. And also, the SGX instruction can be decoded by IDA and Radare. That is good. Now, a bit more about your developer key and the licensing program. You cannot use the real thing easily. You can code and you can try and you can run debug mode enclaves, but they are not secure. Why? You can place a debugger inside, you can hook a debugger, you can see the memory, and you can modify what is happening. Release mode enclaves are secure. You cannot modify what is happening inside, and you cannot read the memory. But you need an Intel approved key. To do this, there is an Intel developer program that you can mail them and you can start the process, and they can give you a key. But you need to sign an NDA, they need to approve you as a developer. So there are some limitations. There were some concerns about this, and it seems there is a major change coming. So the launch enclave might be modified in the way that you could be able to run enclaves without the Intel approval. This is still not in any processor in the market, but it's on the documents and should be coming. When you are developing an enclave application, you need to partition your application in two parts. The untrusted domain, it is the normal application that we always code. It interacts with any external parties, the input-output, the system, and it will also start your enclave. The trusted domain, it's the enclave. It will be the one that executes the protected code and can be seal secrets. The important thing is that the memory of the trusted part is protected and also keeps integrity. You cannot modify what the code is doing. And you can invoke each other. The untrusted domain can call the trusted and the other way around. There are a couple of challenges that you need to determine how to split the trusted and untrusted domains in a way that you minimize the attack surface. And you also need to do extra validations on the untrusted inputs, because now not even the operating system can be trusted. There are some constraints. As I said, you cannot do system calls, and a few instructions are not allowed. Also, the enclave code needs to be statically linked. So all the code is measured and the integrity is kept. You cannot dynamically link against libraries. And the code only runs in user mode. The memory limitations are also set during the enclave signing. This is changing. It's changing on SGX2, but you need to know it. Now, a couple of important things about SGX. You have something called sealing. Sealing is a way to encrypt secrets inside the enclave to store them out. So when you are working with secrets, you sometimes need persistence. You need to distribute them in a way, or you want to keep them in the hard drive, but you want to keep them encrypted. So sealing, it's based on the key derivation from the CPU. The key used for sealing is secret, and it's based on the hash of your enclave and some other things. So, sorry. You can base the key on the enclave, but there are two policies. You can also base the key on the signer identity in the way that any other enclave signed by you can also read the secret material. The keys are also different for debug and production, and you can implement replay protection and time-based policies. The other important component is remote attestation. Remote attestation is the process of ensuring and verifying the enclave integrity from a remote client, and also establish a secure channel between the client and the enclave to provision secrets and communicate. In practice, this is based on another of the hardware keys, and you start doing a handshake in which you get a secret key agreement, and you get what is called a quote from the enclave. That is, it comes with information about who signed the enclave, what is the hash of the enclave, is it running in debug mode or not, and also the security version of the platform. This quote, you have to verify it. You need to trust it by yourself. You need to check who are you communicating with, and you also need to verify the quote against an Intel attestation service that will tell you if that quote is valid or not. If it's valid, you can provision secrets, and you should be safe. And now,
Okay.
Jean-Philippe, please.
Thank you. Okay, so we're about halfway through the talk. A small disclaimer, SGX is really complex, so we went very quickly over the SGX specific at the beginning. So if you're a bit confused, if you never heard about SGX, it's totally normal. So we know it's a lot of information, but we'll release the slide and the white paper so that you can get all the details and sit down to understand everything. Okay, so next part, crypto. So crypto is really super important in SGX. So you need crypto to encrypt, authenticate stuff. And it's maybe one of the most complex use of cryptography I ever used. And I've seen pretty scary stuff. What you just see here is schematics of what's going on the remote attestation process that Luis just described. You don't need to read what's written just to see that you have like 6 entities sending messages to each other. And these messages include cryptographic signatures, diffie-Hellman stuff, symmetric key crypto. And you can imagine that if just one single piece of those is insecure, then maybe everything can break down. So just a very small review of the crypto zoo, what kind of algorithm and schemes are in SGX. Very quickly, you have RSA with a modulus of 3,000 bits. The PKCS standard 1.5, which is not the latest one. It's insecure in certain contexts, but it's apparently not insecure in the context of SGX. It's using the SHA-256 hash function, which is also a federal standard. It uses elliptic curve cryptography, specifically ECDSS signatures using the P256 curves standardized by NIST. It's using elliptic curve diffie-Hellman over the same curve. And most of the symmetric cryptography uses AES, so AES counter for normal encryption, AES GCM for authenticated encryption, and AES in CMAC mode if you just want to tag and don't want to encrypt. Okay. So this all gets you 120-bit security, except for RSA, which gets you approximately 112 bits of security. So that was for the standardized crypto. There's also some custom crypto in SGX. So you may have heard on the internet that custom crypto is bad, do not roll your own crypto, blah, blah, blah. But Intel, they have pretty good cryptographers, they know what they are doing. And they really had at some point to design a custom MAC to be super fast to encrypt the RAM, because you cannot afford too much latency. And it has to be, like I said, in hardware. And there's a new design, I think by Shigeron and other people, that is really nice. They have proof of security. So I do not doubt of the security of this algorithm. It also uses AES counter to encrypt data in memory, a slightly modified version. But we looked at it, and there's no reason to believe that it will be less safe than the standardized version. Okay, let me just. So in the SDK, you've got a couple libraries, libc, and you also have a crypto library. In the Windows SDK, it's called SGX tcrypto.lib and tcrypto.opt.lib. So opt stands for optimize, not optimizing speed, but mainly in space, so the code tends to be smaller. So Intel warns you that, well, it's pretty boring. It's the library might be somewhat limited. And indeed, you only have AES, GCM encounter mode, CMAC, SHA-256, and a T-curve DSA and diffie-Hellman. So these are secure standardized algorithms, but you may need more than that. You got to be careful, though, because the algorithms themselves are secure, but they support weak parameters. So if you tell the counter API to use a 1-bit counter, so which will 0, 1, 0, 1, then it will accept it. It might remind you some other library. So where does this crypto comes from? So they didn't create it from scratch just for SGX. They recycled the IPP, which is Intel's proprietary library. As far as we can understand, it's the version 8.2, labeled Gold, from 2014. You only have the binaries, and to use it, I think you got to get a license from Intel. So maybe SGX is a way to use it without paying the license fee. On Linux, I mean, it was a bit depressing because we started looking at this, I think, in February or March. And we only have the binaries. And then on the 25th of June, here comes the source code with the Linux SDK. So you have a pretty similar library with the same API. It's in the SDK/tlib crypto directory for the SGX wrappers and external crypto for the IPP equivalent. You've also got a bunch of public keys that Intel is using, but they are public, and it's okay if they are public. Because in some applications, a public key should not be public, but here it's fine. And if you look at the code, it's surprisingly well written and quite safe. Like, you have 2 different errors, it will return different error codes. This looks very stupid, but not all libraries do this. And yeah, it's very well written, and yeah, compared to others. I'm looking at OpenSSL. Now, maybe one of the most important algorithms is AES. How is it implemented? So AES might be vulnerable to some side channel attacks, cache timing attacks. The one that I mentioned before, where I said that you can have cache timing vulnerabilities in SGX enclaves. So if you look at the Windows library, it uses the native instructions, AES-NIs, the hardware instructions in the CPUs, to compute the rounds. So AES iterates 10 rounds, and you have an instruction called AES-ENC to encrypt and AES-DEC to decrypt. You also got an instruction called AES-KeyGen assist to perform the key schedule, so the transformation of the key that you use to encrypt or decrypt. But surprisingly, again, as far as we can tell, it's not used in the library of Intel, but instead it's using an implementation based on tables. So the kind of thing that tends to be vulnerable to cache timing attacks. But in these specific implementations, there's some countermeasures to avoid cache timing attacks. On Linux, it's a little bit different. When you look at the source code, the implementation is a textbook implementation, which is very slow. Don't understand why it's done this way. Even the SBox is not the usual table-based implementation, but it's just a simple lookup table with 256 values. But in the enclaves of Intel, the one for which you only got the binaries, they do use the fast instructions. So this is simple of the code where you see that they're trying to access all the cache lines to avoid leaking information on which cache line was accessed. Now, maybe the most important thing in crypto is randomness. So without randomness, you have no security at all because everything becomes predictable. The nice part when we looked at it is that the weak random generators that you have in the libc rounds round, they're not available. You only have one function called SGX read round, which is using the RD round, the read round instructions of the Intel CPU. So that's nice. And Intel warns you that you got to try up to 10 times this instruction because it may fail. They don't really tell you why, but well, I can tell you why later. So you might think, okay, I got to call this function up to 10 times, but no, if you look at how it's implemented, in the library, you actually have this iteration they test it up to 10 times. And if it fails, they return an error code. So you should always check the return value of read round. One funny thing with read round and read seed is that it's the only instructions for which an hypervisor can prevent you from using. I mean, the hypervisor can modify the virtual machine control structure and say every time I see a read round called, I will do a VM exit. So can perform a denial of randomness attack, if you will, but you will notice it because you will have a VM exit. Okay, next. Okay, just be careful if you look at the Linux SDK. There's something called sample libcrypto, but you should not use it because it's very weak, and it's even written in the comments. It's very weak just for testing some stuff. Okay. Now, interesting part. So I mentioned this piece of software, which is the code enclave, which verifies the identity of an enclave of its program, and it signs it using a very specific signature scheme called EPID. I'll talk about it later, and it creates a quote. So in this SGX world, it's equivalent to a public key certificate. But it's using some crypto scheme that is not documented, so we try to look at the binary. And it looks like this. So just look at the boxes, not the errors. You have RSA 2048, AES, this EPID thing, SHA-256, and SHA-256. So each time you create this kind of certificate, it creates a new random key K of 16 bytes and a new random IV of 12 bytes. So if you've been to the talk yesterday about GCM, you might say, aha, you should not use random IVs because it might repeat because of the birthday bound. Here's not a problem because you have a random key every time, so it's okay to have a random IV. And you see that the key is hashed. So what it's doing, essentially, it creates a new symmetric key. It encrypts it using RSA, and it uses this key with ASGCM to encrypt a signature with a random IV. So at the end of the day, in the quote, you get the encrypted key, the encrypted signature, and you get a hash of the key. Okay. Now you get the encrypted key. Well, okay, it's a mess. Anyway, so how secure is this? So I've never seen this kind of scheme before. If you try to abstract the construction, it's actually what's called a hybrid encryption scheme, where you combine a secure public key scheme and a secure private key scheme. So here you combine AES and RSA. So the construction itself looks sound because you have this security notion. You know that OAP, the mode of RSA used here, is INDCCA secure, which means very strong. And you have AES GCM, which is INDCPA and even a bit more. So it also means quite secure. One small caveat is that it leaks the hash of the key. So if the key were too small, you could do some time memory trade-off attacks that you couldn't do without it. Also, you don't get forward secrecy because it's RSA, so if the private key leaks later on, you can decrypt everything. And also what is a bit surprising, so before I mentioned that RSA 3072 was used, and here you just get RSA 2048, so it's equivalent to approximately 90 bits of security only. Okay. Now, EPID very briefly. It would take me like 2 hours to explain all the details, but it's not the signatures you're used to, where you have a signer and a verifier. It's a group signature scheme. So you have a group of possible signers, in this case a group of CPUs with the same TCB version. And each member of this group, they can issue a signature. And when you get a signature, you will only see, okay, one member of the group signed this piece of data. But you will not know which actual CPU signed it. And even the, let's say the master key, the holder of the master keys, Intel in this case, and even the other CPUs, they cannot figure out which actual CPU issued this signature. So why doing this? The whole point, to simplify again, is to prevent the tracking of individual CPUs by looking at the signatures. Okay. So again, we don't have all the details of how it's implemented. We know that there's a research paper where they describe all the details of this scheme. You have security proofs and everything. It's not implemented in microcode because allegedly it's way too complex. You don't have the source code either. It's only in the binaries provided by Intel. So again, it's our point of view on this. But the details of the scheme implemented, they're available publicly. The type of elliptic curve that it uses, it's something called the baryton-arithmetic curve, so a type of curve that is optimized for this type of scheme, which uses cryptographic pairings, but I won't give the details. And you have several ways to implement this. It's very, very complicated. But it seems similar to what is published in this paper where you have the reference. Okay. And again, you don't have the actual parameters. So you cannot directly say it has a 128-bit security level or a 256. Again, you have to trust Intel for this. Okay. And for the last part.
Thank you. So we have been busy doing a few things. We are releasing a couple of them here. There is a cool thing about SGX and crypto applications. It allows you to cheat. You can use the CPU as a key storage, or you can use it as a TCB and implement complex functionalities that are usually slow and quite complex, are fully homomorphic encryption, multi-party computation, a few things that would be complex with classic crypto, but with SGX you can do them easily. So one of the projects we are releasing as a proof of concept, warning, you shouldn't use it in production, it's not review, it's a proof of concept. It's a re-encryption proxy where you simply get a ciphertext and convert it to another ciphertext without exposing the keys nor exposing the plain text. We are only using symmetric keys, and we are using sealing to store the keys used for encryption and decryption, and some policies like which keys can be used together, which clients are allowed to use the keys. So it's an interesting example. The goal is no leaking the plain text, no leaking the secret keys, no leaking the keys involved, the key IDs involved on every re-encryption process, and not leaking the policies. There are a few limitations. The OS may modify your seal blobs, but you will notice the seal blobs have integrity. You don't have a trusted clock. So if you try to implement a key expiration policy, the OS can tell you the wrong time. There is a clock source on SGX. You have a trusted clock, but you don't know the origin of time. It's only relative. It can also, it's not a full clock. And also, we are fetching the keys on every re-encryption request, so the OS can tell which pairs are used together. This is the protocol we have implemented. On the left, we have the laptop. On the right, we have the enclave. So we compose a request in which the client identifies himself with his public key. We tell in the request the key identifiers that we want as input and output, and we give a ciphertext. This request is encrypted. So now that you encrypt the request, anybody in the middle between you and the enclave cannot see what is happening. We send the request to the enclave. We try to decrypt the request with the client public key, and if it's okay, we check the policies, like, can we do this operation? Are these two keys allowed to be used together? Is this client allowed to use this key? And if all this is okay, we decrypt the ciphertext, we encrypt it again with the new key, we compose the response, and we encrypt again the response with the client public key. We give it back, and the client can get the response. The implementation is based on tweet-salt. Why? Because it's compact, it's minimal, it's post-quantum.
No.
It's good enough. But we get a small library with authentication between the client and the enclave. We haven't implemented remote attestation. What happens when you don't have remote attestation? In our case, we authenticate the enclave with a public key. This public key is generated the first time you run the system. This key is also sealed, so it can be retrieved every time you execute the enclave. So you have to do this process in a trusted environment. If the setup is done in a trusted environment, the integrity of the key should be kept. And then we have a couple of interfaces. We have one to register the keys, and we have one to re-encrypt. And the communication in both is encrypted and authenticated. The other project is a small tool for helping analyzing the metadata from the enclaves, the seal blobs, and the quote. So from the enclaves, you can tell the security attributes, who did sign the enclave, the hash. You can also see which are the entry points that can be invoked on the enclave. From the quotes, you can tell the signature. You can tell if the enclave was running in debug mode. You can also see which is the enclave who generated the quote. And with the seal blobs, you can see which was the key policy, if the blob is encrypted to the signer or if it's encrypted to the enclave, if it has additional authenticated data in plain text. So they are small tools, but they are cool. I have a small demo. Here we have the parse enclave running, and we can see here, it will be, yeah. We can see the hash of the enclave. We can see the signature. We can see the public key. The RSA parameters are valid. and then this will move. We can see which are the entry points at the bottom. So all these memory positions can be used to reverse the enclave and analyze what is happening. Now we will see the sealed blobs. In this case, the blob, the policy is the signer, so every other enclave who is signed by the same signer can decrypt this blob. And we can also see there is some additional authenticated data that comes in plain text. And now we can see the quote. There is a signature, there is a lot of data, and at the bottom you can see which is the enclave hash who generated this quote. You can also see who is the signer. And now we will see in a minute the attributes. Yeah, so the quote was generated by a debug mode enclave. So if you are in the platform, you could hook a debugger and get the information that is inside. Remember, debug modes enclaves are not secure. And that is all from me.
Okay. Let me very quickly conclude. So the obligatory black hat conclusions. So description of what SGX does. It allows you to run your code on someone's computer securely. It's very complicated. You have huge attack surface. We're not disclosing any issues, but just showing stuff that you don't have in Intel documentation, and we're releasing some code. Now, briefly open questions. So I really wonder how bad will be the bugs on SGX. I'm quite surprised we haven't seen anyone yet. Also, how will it be adopted by the cloud providers? Will they just use it for their own security, or will you have maybe the opportunity to pay a premium to get SGX as a client? We'll see also whether the board manufacturers will support custom launch enclaves, which means essentially a way to get more control on SGX instead of Intel. For example, open source firmware like Coreboot, they may also support SGX at some point. I think they will. I'm also looking forward SGX 3 or 4 or 5 supporting the post-quantum crypto that NIST will release in 5 years. So we've got a couple of references. The slides will be online. We have the references of prior work. We hadn't had time to present this. We really had so much time. And yeah, so thank you. And that was the very first talk of Luis at the conference. So I think it did a good job. So. Thank you.